In this screencast, we are going to talk about ionic compounds, which we introduced in the previous screencast. And we are also going to talk about how to name ionic compounds or the nomenclature of ionic compounds. So just as a brief review, ionic compounds are made of a metal and a non-metal. They're held together by different charges. Metals form cations, which are positively charged, and nonmetals form anions, which are negatively charged. We describe this kind of complex as a formula unit, and that's just the smallest electrically neutral unit of an ionic compound. Now, and I want to remind you, the charges on ions depend on the location of the ion of the atom in the periodic table. Right? So for example, group 1 metals form positive 1 and group 2 metals form positive 2. And we can see that here. So I want you to notice everything in this group 1, the alkali metals, form a +1. Everything in group 2, which are the alkali earth metals, form a +2. Now, you're going to notice, and in this kind of first transition metal, they form +3. You're going to notice here in the transition metals that we have multiple charges on some things. We're going to ignore those right now and focus on the things that don't have multiple charges. So right here, we have +3. And then I want you to notice here, aluminum also has a +3. And then zinc, cadmium, and silver, which is kind of like right here. I like to view this as the boot of the periodic table. Kind of looks like a boot. Has just one charge. Zinc and cadmium are +2, silver is +1. Now, metals form positive charges, and so let's go and look at our non-metals. We ignore the noble gases. They're famously unreactive. They already have a full octet. So we're going to start here with our halogens, and they all have a -1. And then we kind of count in on the periodic table. The chalcogens, or the group 16 here, have a -2. And then over here in group 15, we've got a -3. So these are our charges that we are working on. I want to talk a little bit more about how to name these compounds. You are already familiar probably with how to name ionic compounds. When we talk about ionic compounds and naming them, I always go back to sodium chloride, which is table salt, and it's NaCl. And when I was a student, when I used to think about the rules of how to name ionic compounds, when I got my periodic table on the exam, I would always write sodium chloride NaCl. So this would help me remember the rules. And so I want you to look at that and another example here as we're going through the rules. Ionic compounds consist of cations, usually metals. There's going to be a few exceptions, and we'll talk about those. But most often it's metals and anions, which are usually nonmetals. And so I would have sodium here, and I would know that sodium is a metal, and then chloride is a nonmetal. And so I would say, okay, hey, look, I know that this is ionic. That's how I tell. Then the cation is named first using the name of the element. Well, I know that metals form positive charges. They lose electrons. And so that's my cation. It comes first, both in the name and the formula. And so there is sodium. And then the anion is named by dropping the ending of the element on the periodic table and adding IDE as a suffix to the name of the element. So we don't call NaCl sodium chlorine, we call it sodium chloride. And then my nonmetal, of course, is negatively charged there. Now, a few things to be aware of when we look at magnesium chloride, for example. So we have magnesium chloride. When we write these formulas, the charges, these formula units, the charges have to cancel each other, or they have to add up so that they equal 0. So for example, when we look at the periodic table, we see that magnesium is in the alkali earth metals. It's in the second group. So it's going to have a +2 charge. We look and we see that chlorine is in the halogens, and so it's going to have a negative charge. So to figure out the charges, look at the periodic table. Okay, so we're going to look at the periodic table, and we know our charges and we see them here. And when you write the formula, you need to make sure that all the charges of the nonmetals, right, or all the charges of the anions, all the negative charges, equal all the positive charges. So magnesium has a +2, chlorine has a -1. Those don't equal. If you add them up, that gives us a +1. That's not neutral or 0. So that means we need a second chlorine. When we add all the charges up here, that gives us -2. When we add the charge here, that gives us +2. When we add those together, that gives us 0, and that's neutral. And so what we do when we write the compound is we say, great, we need 1 magnesium. Now we're not going to put a 1 there. It's understood. But we do need to put a 2 because we require 2 chlorines. There is another way to do this. If you look here, you can come over here and go magnesium has a 2+ charge. Chlorine has a negative charge. And if you take the charge and make it the number of atoms, so we crisscross, I like to say crisscross applesauce, but if we crisscross those charges to become atoms, right, that becomes magnesium chloride, just like that. Now, there is a caveat if you use this method. Sometimes you have to reduce. These have to be, the number of atoms have to be in the lowest whole number. So for example, let's look at calcium oxide. When we look at the periodic table, calcium has a +2, oxygen has a -2. Those charges, when added together, equal 0, so they're neutral. So if we were to write that, it would look like this, calcium oxide. Totally fine. If we use the crisscross applesauce method and crisscross these down just like this, you end up with calcium 2, oxygen 2. Those are not the lowest whole numbers because you can divide 2 into 2 and get 1. And so you have to reduce to get the correct answer. And that's calcium oxide. There are multiple ways to solve a problem, right? Not just one way. So use whichever way you feel most comfortable with. There's not, like I said, there's not one way that's necessarily better than the other. Now, so we've talked about naming ionic compounds, and I want to get into Roman numerals for just a second. So sometimes those transition metals can have multiple charges. When they have multiple charges, we need to distinguish in the naming whether they have a +2 or a +3. There are 2 ways to do this. One way is the classical system. And what the classical system does is it uses the Latin name of the metal modified with suffixes. Okay, so for example, the Latin name of iron is has this fair here, right? And then we have suffixes. And if it's OUS, right, it's the lower charge. And if it's IC as the suffix, it is the higher charge. So we can have ferrous or ferric, cuprous or cupric. And so you can see here, right, CuCl would be cuprous chloride. That would indicate the cuprous there is that it's copper with a charge of +1, or cupric chloride, which is copper with a charge of +2. For a lot of reasons, the fact that people easily got these confused, there is another system which is called the stock system. It's the system that I personally prefer. And in the stock system, the name of the cation is the name of the element with a Roman numeral in parentheses equal to the charge. And so just like these are the same exact examples on the previous slide. So you can go back and look and compare. I can't go back and forth or the screencast will cut off. But what you see here is we've got iron 2. That 2 is the +2 charge. Iron 3. That 3 is the +3 charge. And you can see here copper 1 chloride. And then, and I don't know why that came down here, copper 2 chloride. The way that I remember that the Roman numeral stands for the charge is I think of Roman soldiers and how they used to charge into battle. And that reminds me, look, this number here is not the number of atoms. It's the charge because Romans charged into battle. All right. I went too far over. So if that kind of broke up there, you haven't missed anything, it just went over. So I want us to practice naming compounds. So let's start off with CrCl3, okay? When we look to name this, we see the cation here, the first thing, the metal. First off, we look at this and say, look, it's a metal and a non-metal. That means it's an ionic compound. That's your first step always, ionic compound. Then we say, look, the cation here is chromium, and the anion is chloride. Now, chromium is one of those cations that can have multiple charges. It's not a group 1, 2, or 3. It's not in the boot or aluminum. So that's how we recognize, hey, look, that can have multiple charges. When that happens, right, chromium here can have multiple charges. So you need to start with the non-metal, okay? And so you start with the non-metal and you need to look at the periodic table to determine the charge. And so I go to my periodic table and I say, okay, hey, look, I know chlorine has a negative charge. And I can see from this compound, there are 3 chlorines right there. So that means chromium here, where we don't know the charge, we know it has to equal or cancel out -3, right? Not equal -3, cancel out -3, because the positive charges have to add to those negative charges to equal 0. So the only thing that can be is +3. So that means when we look at this, we say, great, that's chromium 3 chloride. Okay. Okay, let's do another one. Let's come over here and do another example. Let's look at copper. I want to do it the other way. Let's look at copper with oxygen. Okay. When we look at this, we look at copper and we say, great, we know that's going to be the first word because it's a metal. Okay. And this is a metal and a non-metal. And so these are ionic compounds. And we know that copper is not a group 1, 2, 3, or in the boot, or aluminum. So that means it can have multiple charges. When this happens, we start with the non-metal. So we look over at oxygen, we go to the periodic table, and we say, look, oxygen, right, has a -2 charge. And I want to erase that copper there because I want to move it down. I don't like the placement of it. Okay, so let's move that copper down here. So oxygen, when I look at the periodic table, it's got a -2 charge. In this instance, we have 2 copper complexes. So when we look at the charges here, whatever these 2 copper charges are, they have to add up to cancel out the -2 on the oxygen. So that means they have to add up to give you +2 to cancel that out. So that means this copper is +1, this copper is +1 to give us +2. So that then is copper oxide, just like that. Now, if you have the Roman numeral and you're going from the name to the complex, this is awesome because you look at this and you say, hey, look, copper, it gives you the charge is +2. And then oxygen here, you look at the periodic table, it's -2, right? Crisscross applesauce down. That's Cu2O2, and then you reduce, and that gives you CuO. Okay. If we look at this and, for example, another one, for example, would be zinc nitride. Okay. Here, zinc is in the boot, so it doesn't get a Roman numeral. So you have to look at the periodic table. You have to say, okay, hey, look, I know zinc has a +2 charge. And nitride, that's nitrogen. It's derived from nitrogen. And I know it's got a -3 charge. Right? You crisscross applesauce those down, and you get N2. Okay? So zinc 3, N2. Now, another thing that we run into with ionic complexes are something called polyatomic ions. When we look at poly, the prefix here means many, okay? And so these polyatomic ions are many atoms and the whole thing has a charge. So for example, if we look at sulfate, it is SO4 2-. It always comes as a package. It always comes together. And this entire thing here, with all these atoms together, is -2. Now, here is kind of the Debbie Downer about polyatomic ions. You have to memorize them. And so I'll give you a chart in class, but you have to commit them to memory. Now, there are some trends that can help us with this. And so, for example, right, I want you to think about nitrite and nitrate here, and then sulfite and sulfate, and then this chart doesn't have phosphite on it for some reason. Wonder if it got cut off. Well, I'll give it to you in class. Look at chlorite and chlorate. Okay, those are the three. When we look at this, I want you to notice these are called oxoanions. They're just polyatomic anions that have oxygen. Okay, and there's lots of them. But when they have the same name, I want you to notice between the ite and the ate, the ate always has one additional oxygen. Okay, we like to say that the sulfate ate an extra oxygen. Notice the charges stay the same, right? The charges aren't going to change. The only difference between these is that there's an extra oxygen there. So let's write down kind of what I said on the previous slide with these oxoanions. These are just polyatomic anions that contain oxygen, right, with other elements. Most of these, right, the difference here is ate and ite. And so if they're kind of related, and so it's really important to see that ate has one more oxygen than ite. Now, the other thing that you're going to see is the prefix per, and it means one more oxygen. So look at this. You have chlorite, chlorate, which has one more. And then if you've got a per, it means you've got even one more. And then hypo means one less. And so you can see there's one less oxygen here. So we can also use our knowledge of prefixes to help us. So let's practice naming some of these guys. Let's look at ammonia nitrate. So if you have ammonium nitrate, okay, what you do is you've got these polyatomic ions memorized, and the cation here is ammonium. It's NH4 plus, and then the nitrate here is NO3 minus. You crisscross these down, and you see that you have NH4 NO3. Okay. I want to point out something. This is the one exception to, well, there's another exception, but this is the exception to ionic complexes being metals and nonmetals. Ammonium is the exception to that. Now, in this case, both of these polyatomic ions there's just one of them. But you are also going to have situations where there's more than one. So, for example, let's look at chromium 3 perchlorate. When we look at this, it's got a Roman numeral, and so that's really helpful. That tells us, hey, look, it's going to be chromium 3 plus. And then when we look at perchlorate, we've memorized perchlorate, and so we know it's ClO4 minus. So when we go here to crisscross, right, we end up with 1 chromium, but we are going to have 3 chlorates. And so if you have more than one polyatomic ion, you need to use parentheses because you're tripling this whole thing. It acts like a package. It stays together. So if you have more than one polyatomic ion, use parentheses. Okay? And so that's what we see there. Now, I want to hit on acids just really quickly. We are going to look at some reactions of acids and bases. And so to help you with that, it's helpful if you recognize acids. When we look at acids, One type of acid contains a hydrogen and a monoatomic anion. And that hydrogen, a really good way to look at that and notice that is that hydrogen is right out there in front. Okay, right there. And so when we look at these names, if you saw HF together, you might think, okay, that's hydrogen fluoride, that's a molecular name. But because it's got that H out front and it has some kind of unique properties because it's an acid, it gets a special name. And so it's hydrofluoric acid. If it's just an H and a monoatomic ion, use the prefix hydro, the halogen base name, and then the suffix ic, and then the word acid. So HBr is hydrobromic acid. Now, there are other acids that are based on oxoanions. So here are some examples. We've got sulfuric acid here, and then, for example, sulfurous acid here. Notice that if the oxoanion name ends in ATE, then the corresponding acid is going to be IC. So that's sulfate, and so it's SO4, and then sulfite is SO3, 2 minus. And so it's going to be the sulfurous acid. We normally use the ic acids more, so phosphoric, nitric, sulfuric, more than the ones that are ose acids. But it's helpful to see. The other thing I want to point out is each of these has that hydrogen in the front, and so that hydrogen in the front screams it's an acid to us. And so we'll talk more about that in our acid and base chapter, but I did want to go ahead and introduce that topic here. Okay, so we've done a lot. I know naming ionic compounds. There's just a lot. There's Roman numerals, there are rules, there are polyatomic ions. We name acids differently. Practice is the best way to get really good at this. And of course, I'm happy to help. Please stop by my office and we can work all the problems.